Close your eyes and transport yourself back to the turn of the 20th century. We are in Great Britain, the beating heart of the Industrial Revolution. The air is thick, tasting of coal dust and sulfur. The soundscape is a deafening symphony of clanging hammers, hissing steam, and the rhythmic thud of drop forges. We are standing inside one of the great railway workshops, perhaps Swindon, Crewe, or Stratford. These weren't just factories. They were cathedrals of soot and steel, vast industrial cities where raw metal was beaten into the locomotives that powered an empire. But within these congested, labyrinthine complexes, the engineers faced a logistical nightmare. It was a problem of geometry and physics. They needed to move massive components, boiler shells, wheel sets, the heavy castings, through spaces that were simply too tight for traditional cranes, yet far too heavy for manual labor. The overhead gantries were stuck on fixed rails high above. The standard shunting engines could push wagons, but they couldn't lift a single pound off the ground. There was a gap in the machinery of the age. The solution they devised was a mechanical Frankenstein, a machine that defied categorization. It was part locomotive, part lifting gear, and entirely unique. This is the untold story of the crane tank. Part 1, The Genesis of Necessity. To truly understand why the crane tank was invented, we have to look at the floor plan of a Victorian railway works. Space was the ultimate luxury, and it was a luxury these workshops did not have. Tracks were laid dangerously close together to maximize capacity. Buildings were packed tight, connected by low arches and narrow alleyways. Imagine you are a foreman at the Great Western Railway. You have a 3-ton boiler shell sitting in the foundry. It needs to get to the erection shop, which is 3 buildings away, across a busy yard, and through a tunnel with low clearance. The big overhead cranes are useless. They are bolted to the roof of the foundry. You can't take the roof with you. The standard shunting engines, the small, boxy locomotives used to push trains, are plentiful, but they are strictly horizontal movers. They can push a flatbed truck to the door, but who loads the boiler onto the truck? In the 1860s, this bottleneck meant armies of men with block and tackle pulleys, dangerous makeshift ramps, and hours of wasted time. It was inefficient, and in the Victorian era, why inefficiency was a sin. The engineers looked at their shunting engines, and they looked at their steam cranes, and they asked a simple radical question: why not bolt the crane directly onto the locomotive? The concept was brilliant in its simplicity. They wanted to create a self-propelled lifting device that utilized the existing rail network that crisscrossed the yard. It needed to shunt wagons like a train, but lift like a crane. Crucially, it had to be powered by a single source, one boiler, one fire, doing 2 jobs. Thus, in the industrial haze of the 1870s, the concept of the crane tank was born. It was a machine born not of vanity, but of pure, desperate necessity. Part 2, Anatomy of a Hybrid. Now you might think building one of these machines was as simple as welding a crane jib onto the front of a train. It was not. In fact, it required a complete rethinking of locomotive physics. To understand why, we have to talk about the conflicting nature of these 2 machines. A standard steam locomotive is designed for traction. Its job is to pull weight horizontally. It needs to be balanced, with its weight distributed evenly across its wheels to grip the rails. A crane, however, is designed for stability. Its job is to lift weight vertically and swing it around. When you hang a 6-ton weight off the side of a machine, you are actively trying to tip that machine over. Combining these 2 functions created a violent conflict of physics. First, there was the center of gravity. Mounting a heavy crane mechanism, the jib, the massive iron chains, the reduction gears, and the lifting cylinders, raised the engine's center of gravity significantly. These machines became top-heavy. On the narrow, often uneven temporary tracks of a shipyard or a workshop, they were prone to rolling over. Second, there was the issue of axle loading. The weight of the crane was usually situated at the rear or the center of the locomotive. If you took a standard 4-wheeled shunter and dumped a crane on the back, the engine would rear up like a frightened horse. The engineers had to adapt. The typical solution, pioneered by the North London Railway in 1872, was the adaptation of the tank engine. For those who don't know, a tank engine carries its water and coal on board the locomotive itself, rather than pulling a separate tender behind it. Engineers would take a standard 040 tank engine, that's 4 driving wheels, and extend the heavy steel frames backward. They added a trailing axle, on creating a 042 wheel arrangement. This extra set of small wheels at the rear was critical. It acted like a shelf, supporting the immense weight of the crane gear and the counterbalance weights needed to keep the engine from tipping when it picked up a load. Then, there was the power distribution. A crane tank didn't have a separate engine for the crane. It was a parasite. Steam was drawn from the locomotive's main boiler via a high-pressure manifold. This steam was piped into a pair of small, rapid-fire auxiliary cylinders that drove the winding drum to lift the hook and the slewing gear to rotate the jib. The result was a machine that looked like a mistake. It was compact, often ugly, bristling with levers and chains, and utterly bizarre to behold. But it worked. Part 3, the timeline of innovation. The timeline of the crane tank mirrors the golden age of British steam power. It starts with experimentation and ends with heavy-duty dominance. It began in 1872 with the North London Railway. Their Bow Works facility was notoriously cramped. They took the leap first. They converted a standard shunting engine into a 042 crane tank. It was a prototype, a proof of concept. But when the workers saw it effortlessly lift wheel sets and ferry them between the machine shop and the carriage sheds, they knew the future had arrived. But the true giants of this story emerged later, between 1881 and 1922, at the legendary Swindon Works of the Great Western Railway. The Great Western Railway, or GWR, was famous for its engineering ambition. Under the legacy of Isambard Kingdom Brunel, they didn't do things by halves. At Swindon, they needed beasts of burden. In 1881, the GWR began converting former broad-gauge engines into standard-gauge crane tanks. This was a statement of intent. They were recycling old technology to meet new industrial demands. But the peak of the era came in 1901. This was the year Swindon engineers took 2 Panny-class tank engines and fitted them with massive cranes capable of lifting 6 tons. They gave these machines names, and not just any names. They chose names from mythology. They christened them Cyclops and Titus. Giving these industrial machines such grand names highlights the respect the workforce had for them. They were the strongmen of the yard. They were the titans. Decades later, in 1922, as locomotives grew larger and the parts became heavier, a third engine joined the fleet. They named him Hercules. For over 30 years, Cyclops, Titus, and Hercules were the undisputed kings of Swindon. They were the only machines in existence capable of lifting a massive boiler shell, placing it onto a flatbed, pushing that flatbed to the next building, and unloading it, all without a single manual lift. They were the indispensable muscle of the railway. Part 4, Variations on a Theme. While the Great Western Railway favored the brute force approach, other manufacturers across Britain developed elegant and sometimes eccentric variations to solve their specific problems. Let's look at the design from Neilson and Company. This is perhaps the strangest of them all. Neilson wanted to keep the locomotive as short as possible to navigate extremely tight turns in factory yards. Their solution? They mounted the crane concentrically around the funnel. Picture this. The crane jib pivoted around the smokestack itself. The chimney was the axis. While this was a marvel of space-saving engineering, it was a nightmare for the crew. The hot exhaust gases and smoke from the chimney blasted directly into the crane gear, heating the metal and choking the operator. Visibility was often zero. Yet, it remains a fascinating example of Victorian, compact engineering, solving a problem regardless of the comfort of the human operator. Then there was the folding hook design by Robert Stephenson and Hawthorne's. Some workshops had very low doorways. A standard crane jib sticking up in the air would smash into the lintel of the door. So Stephenson's firm designed crane tanks with folding jibs. The crane arm could be lowered flat against the boiler or the roof of the cab when the engine was traveling. It allowed the engine to duck under low bridges and enter warehouse doors like a tortoise pulling in its head, only to deploy the crane like a robotic arm once it was safely inside. However, the most successful and widely copied design came from Dubs and Company of Glasgow. They perfected the slewing crane. They mounted the crane mechanism behind the chimney but in front of the cab. This design allowed the jib to swing a full 360 degrees, at least in theory. In practice, they usually limited the swing to prevent the jib from smashing into the driver's cab. This design offered the best balance between lifting capacity and visibility, and it became the industry standard. Part 5. The operational reality. So, we know what they looked like, but what was it like to actually operate a crane tank? Based on historical accounts and the few surviving manuals, it was a job requiring immense skill, physical strength, and nerves of steel. First, there was the bunker trade-off. To make room for the massive crane machinery on the back or sides of the engine, something had to be sacrificed. Usually, that sacrifice was the coal bunker. Crane tanks had notoriously small coal capacities. They suffered from what we might call today range anxiety. They couldn't travel far from the coal stage without running empty. However, since these engines lived their entire lives within a 5-mile radius of a workshop, this was a manageable annoyance, but it meant the crews were constantly refueling, and often handballing coal into tiny side pockets while the crane was stationary. Then there was the stability dance. Lifting 6 tons with a locomotive is inherently dangerous. If the jib was swung out at a 90-degree angle to the track, what they called a broadside lift, the leverage could easily tip the engine over. To combat this, many crane tanks were fitted with rail clamps. These were heavy mechanical clips that the crew had to deploy to lock the locomotive chassis to the steel track before a lift began. For the heaviest lifts, the procedure was even more crude. The crew would have to jam timber blocks between the axle boxes and the frame of the engine. This stopped the suspension springs from compressing, effectively turning the locomotive into a solid, rigid foundation. Finally, consider the crew itself. This wasn't a standard 2-man job. Unlike mainline trains with just a driver and a fireman, crane tanks often required a third specialist, the slinger. The ecosystem of the cab was crowded. The driver managed the boiler pressure and moved the locomotive along the rails. The crane operator, often the driver or fireman doubling up, used a separate set of levers to control the steam flow to the crane cylinders. And outside, on the ground, was the slinger. He was the eyes of the operation. He attached the heavy chains to the load, checked the balance, and used a complex language of hand signals to guide the lift. It was a symphony of steam and steel. A slight mistake in communication, a misunderstood hand signal, or a slip on the throttle could result in a crushed wagon, a dropped boiler, or a derailed engine. Here's Part 6, the twilight of the steam crane. The reign of the crane tank was long. For nearly 60 years, they were the kings of the workshop, but their demise was inevitable. The catalyst for their extinction was not a better train. It was the evolution of the road vehicle. By the 1930s, the internal combustion engine was becoming powerful and reliable. The mobile road crane emerged on the scene. The road crane offered things the crane tank could never compete with. First, flexibility. A road crane could drive anywhere. It wasn't tethered to the rails. It could drive inside a workshop, turn around in a tight corner, and drive out the other side. Second, readiness. A steam crane tank took 3 hours to raise steam from cold water. You had to light a fire and wait. A diesel road crane started with the turn of a crank or the twist of a key. And third, safety. Road cranes had outriggers, stabilizing legs that extended out to provide a wide, solid base, far wider than the narrow gauge of a railway track. The end came swiftly for the giants. In 1936, the Great Western Railway made the hard decision. Cyclops, Titus, and Hercules were withdrawn. Their boilers were tired, their frames were stressed, and their function could be performed better by the new diesel machines. They were cut up for scrap. It was an ignoble end for the machines that had literally built the GWR fleet. They were melted down, perhaps to become the very rails they once rode upon. By the start of World War II, the crane tank was largely considered obsolete technology. A few soldiered on in private shipyards and smaller industrial facilities where the cost of paving roads was too high, but their golden age was over. Part 7. Legacy and Preservation. Despite their obsolescence, the crane tank holds a special place in engineering history. They represent a specific moment in time, a moment when the railway was the solution to every problem. Did you need to move people? Use a train? Did you need to move coal? Use a train. Did you need to lift a boiler vertically into the air? Well, let's build a train that can do that too. Fortunately, all is not lost. The preservation movement of the 1960s and 70s managed to save a handful of these unique machines from the cutter's torch. Today, preserved crane tanks can still be found at museums and heritage lines across the UK, such as the Foxfield Railway or the Bressingham Steam Museum. Seeing a crane tank in action today is a revelation. It is a sensory experience. It is a mass of hissing pipes, spinning gears, clanking chains, and puffs of steam. It demonstrates visually the mechanical complexity of steam power in a way that a streamlined express train simply cannot. You can see the muscles working, you can see the gears turning. So, why do they matter? The crane tank is the ultimate example of Victorian pragmatism. They were not built to be beautiful, they were built to work. They were ugly, they were top-heavy, and they were difficult to maintain. Yet, they persisted for nearly a century because they solved a problem no other machine could. They serve as a reminder that innovation is not always about going faster or looking sleeker, or being more digital. Sometimes innovation is about taking two existing technologies, a train and a crane, and bolting them together to get the job done. Summary of technical characteristics. For the enthusiasts listening who want to visualize the specs of these machines, let's break down the archetype of the crane tank. Most of them utilized a 040T or 042T wheel arrangement. That T stands for tank engine. The trailing axle on the 042 was the secret weapon, providing the crucial support for the crane's weight. The power source was a single boiler using saturated steam. It was a shared heart, pumping life into both the propulsion cylinders for the wheels and the lifting cylinders for the crane. In terms of strength, they punched well above their weight. The lifting capacity generally ranged from 2 to 6 tons. The GWR Cyclops class hit that upper limit, capable of lifting massive loads, though the capacity dropped the further out you swung the arm. The lifting radius was typically tight, about 12 to 18 feet. These were close-quarters combatants, not long-range artillery. And inside the cab? It was a dual-control nightmare. You had the regulator and reverser for driving the train, and a separate set of hoist and slew levers for operating the crane. It was a machine that demanded a master's touch. Conclusion. The story of the Victorian crane tank is more than just a curiosity of rail history. It chronicles a distinct lineage of industrial evolution. From the pioneering experiments of the North London Railway to the heavy-lifting titans of Swindon, these machines were the unsung heroes of the railway age. They built the engines that pulled the famous expresses, they loaded the goods that fueled the economy, and when their time passed, they quietly rusted away, replaced by the rubber tire and the diesel engine. To look at a crane tank is to look at the Victorian mind at work. Ambitious, heavy-handed, perhaps a little dangerous, but brilliantly functional. They remain to this day the weirdest and most wonderful hybrids to ever grace the rails.